Hello and welcome to Cruising Through Calculus. My name is Alex and today we're going to be going through the limit guide. Looking back at limits, there are actually quite a few things you need to know. So to help you out, I've created a flowchart. Now, when you first look at this flowchart, it looks pretty intimidating, but that's only because there's a lot of different things that can happen with limits. The whole purpose of this video is to basically just go through this flowchart with you. So feel free to follow along with the flowchart as we go through it, and you can see how it'll help you find the answers that you're looking for. An important thing to note is that I can't put down every single answer for every single limit problem that you'll run into. But what I can do is guide you along the path that can lead you in the right direction. So with that said, why don't we start? The very first thing you want to do is to analyze the limit part of the question that you're looking at here. And you're going to find that there are two things that will happen. Either the limit will be approaching infinity, or you will be approaching just a number. We're going to look at the first scenario here where you're approaching just a number. When you're doing limits as x approaches a number, the very first thing you want to do is substitution, which really just means take the value that you are approaching and plug it into your function and see what happens. When you do this, one of three things will happen. The first thing that will happen is you will get a number, which essentially means that will be your answer. The second thing that will happen is you will get 0 over 0. And the third thing that can happen is you will get not 0 over 0. We will be going through each one of these. Let's start with the first one, a number. Consider the following example here. The limit as x approaches 1 of x minus 1 over x. Well, the first thing I want to do is substitute. So I'm going to take the value that we're approaching and simply plug it in for x. So we get 1 minus 1 over 1, which is 0 divided by 1. And 0 divided by anything other than 0 is simply 0. And since we ended up with a number, this is our answer here. Now the reason why I chose this problem in particular is because I want to differentiate between this 0 here in the numerator and these other two examples where 0 is in the denominator. You should always remember that having a 0 in the numerator is okay, but something weird is happening when there's a 0 in the denominator, which is why we have to change up our thinking a little bit when we run into these other two situations. Now when you do substitution and you get 0 over 0, there are a lot of different things that can happen. We're going to look at 5 different methods that you can use. So depending on what you see, that's what you'll use. That means that when you get 0 over 0, the very first thing you'll want to do is actually analyze the function that you're looking at. So let's consider this function down here. First, let's make sure we do get 0 over 0 when we plug 3 in. In the denominator, we're going to get 3 squared minus 9, which is definitely 0. Up here, we're going to get 3 squared minus 3, which is 6, minus 6, which is 0. So we do get 0 over 0. Now, when I look at this function here, the very first thing that comes to my mind is that this is factorable. At least the numerator and denominators are factorable. And so this is the first method that we're going to be looking at. If you can factor something that gives you 0 over 0, that's what you should do. So let's go ahead and let's factor this. In the numerator, we need to find what multiplies to negative 6 and adds to negative 1. That will be negative 3 and positive 2. In the denominator, this is a difference of squares, so we're going to get x plus 3, x minus 3. Now notice that when we do this, we have an x minus 3 and an x minus 3. So these are common factors that will cancel out. This is perfect because x was approaching 3. And remember, we got 0 over 0. So what we've done here is we've eliminated that 0 over 0 aspect. Now we have x plus 2 over x plus 3. We can simply go back to substitution now and plug 3 in. So we're going to get 3 plus 2, which is 5, and then 3 plus 3, which is 6. And since we finally ended up with just a number, we have our answer. The next thing you'll want to be on the lookout for when you get 0 over 0 are square roots in your function. The moment you see square roots in your function, that means you're going to use the conjugate method here. So notice that if we do plug 4 in for x, we do indeed get 0 over 0. We have the square root of 4 minus 2, which is 0, and 4 minus 4, which is 0. Now, you can't factor this, which is why we have to use the other method, the conjugate method. So what we're going to do is we're going to multiply by the conjugate. That is the part that has the square root in it. Now keep in mind that when you do this, you only need to change the middle sign. So whatever this is here, flip it. Otherwise, keep the first piece and the last piece the same. So let's see what happens when we multiply this out. In the numerator here, we're going to FOIL. So we have the square root of x times the square root of x, which we'll say is x. We have the square root of x times 2, which is 2 root x. Then we'll have negative 2 times the square root of x. Those two terms are going to cancel here because one is positive and the other is negative. And then we have negative 2 times 2, which is simply negative 4 here. So that middle piece will be gone, just like that. Now, here's a tip for you. When you're doing these problems and you multiply by the conjugate, do not FOIL the other side. Just leave it exactly like it is. X minus 4, the square root of x plus 2 in this case. The reason you're going to do that is because if you look up here in the numerator, now that these are canceled, we also have an x minus 4 here. So let me write that out down here so it's a little bit more clear. We have the x minus 4 in the numerator. We have the x minus 4, which we did not FOIL out, which means it's very easy to see now that this will cancel with this. And with those two gone, we can now try to find our limit. So we have the square root of x plus 2 here. Now let's see, our x is approaching 4, so all we have to do is plug 4 in for x now. So that'll be 1/4 is our answer here. This is kind of like the factoring method in the sense that once we manipulated it, a common term, a common factor from the numerator and denominator appeared and we were able to cancel them. These were the problem pieces here, if you will, because x is approaching 4, and if you plug 4 into these pieces here, you get, well, 0 over 0. So by eliminating them, we're able to use the substitution method and get our answer. The next thing you want to be on the lookout for are complex fractions. I think of these as fractions within fractions. And if you look at this problem, I think you'll agree that's what we have here. First, let's double check and see what happens when we plug 0 in. We're going to get 1 over 5 minus 1 over 5, which is 0, over 0. So we do indeed get the 0 over 0. So what do we do in this case? Well, what we're going to do now is we're going to focus on trying to get this from multiple fractions into one single big fraction here. In order to do that, we're going to get a common denominator here. There's a couple different ways you can do that, but here's how I like to do it. First, I like to separate the top from the bottom here. The bottom is very simply x, and I won't really need to do anything with that, but I will need to do things up here in this top piece. So in order to get a common denominator, what I'm going to do is I'm going to multiply this side over here by 5 plus x over 5 plus x, and then over here, this needs a 5 over 5. So let's see what happens when we do that. Over here, we're going to get 5. Over here, we're going to get 5 plus x. Now, there is a minus sign here, so what I'm going to do is I'm going to write it like this. 5 minus, and then in parentheses, 5 plus x. The denominator, because these are going to be the same when we multiply them, is simply going to be 5 times 5 plus x. And of course, we can't forget that in the denominator here, we have our x. Okay, so if we take this negative here and we distribute it, we're going to get 5 minus 5. So that means that these 5s are going to be gone, and we're just going to have a negative x up there. Now I'm going to write that down in a second, but there's one other thing that I also want to do. I said we weren't going to do very much in the denominator, and that's true. What I am going to do is I'm going to make this x over 1 like this, and then I'm going to treat it just like I would any other fraction when you're dividing, which is I'm going to multiply by the reciprocal. So let's do that here. First, the 5s are gone. The negative has been attributed to that x there. We have 5 plus x, and then we're going to multiply by the reciprocal here. So it's going to be multiplied by 1 over x. Now, when we do this, I think it's a lot more clear that this x will cancel with this x here. Remember that it's just the x's that are canceling. The negative is still going to be along for the ride. So what we're going to get is a negative 1 in the numerator, and then the 5 plus x in the denominator. At this point, we can use substitution. We can see what happens when x is approaching 0 by simply plugging 0 in for x. So this is going to be negative 1, and then we're going to have 5 times 5 down here, so that'll be 25 like that. Again, this is just like the previous methods. We're manipulating it such that there's some point here when something will cancel out. Just like last time, you'll notice that the terms that cancel out here are the problem pieces. We are approaching 0 here, and if I did plug 0 in here and here, I would get 0 over 0. By eliminating those, we're able to use the substitution method here and get our answer. The next thing you're likely to see are trig functions here. So if you look at this function down here, you'll immediately see we have a tangent here, so we have trig functions. In order to answer these, there are a couple of things you need to know. First, there are two limits that you essentially need to have memorized, and that's these two here. The limit as x approaches 0 of sine x over x is equal to 1, and the limit as x approaches 0 of 1 minus cosine x all over x is equal to 0. Most of the time, what your goal is to take whatever the function is you're looking at and try to make it look like one of these. Now, while you're doing that, there are a lot of different trig things you can do. I'll walk you through what happens on this one. One of the big trig things that you'll do very often is to take things and write them in terms of sine and cosine. We have a tangent here, so I'm going to take that tangent and turn it into sine over cosine. Now, just like in the last example, we have all of this over x. So I'm going to think of this as x over 1, and then I'm going to multiply by the reciprocal. When I do that, what I'm going to get is sine x over cosine x times 1 over x. Now, it seems like we haven't done very much. If anything, maybe we've made it even more complicated. But actually, we're very close to being done with this problem, believe it or not. That's because if I take this and I just rearrange it a little bit, I think it'll be obvious what needs to happen here. So what I'm going to do is I'm going to take these denominators here and I'm going to swap them, which is perfectly fine to do because you can always swap two things that are being multiplied and you'll always get the same answer. Now the reason why I'm doing that is because right here you'll see we have sine x over x, which is right here. That's exactly what we want. This piece over here isn't going to be much of a problem because when we substitute 0 in for x, the cosine of 0 is equal to 1. So we're not going to get a 0 in the denominator. In fact, what we are going to get is 1 times 1, which is simply 1, and that's our final answer. The next thing we're going to look at are absolute value functions. Now, there are a lot of different absolute value functions that could be thrown at you. We're going to look at one particular case that seems to show up pretty often in calculus. That is, the numerator and denominator have the same pieces, but one of them has the absolute value around it. There's going to be one of two answers depending on what you see. Either it's going to be does not exist, or it's going to be some multiple of 1. So let me show you. In the first situation, we're going to be just approaching a number. As you'll see, in the next two examples, we're going to be approaching from the left and from the right. So depending on what one of these three things happens, will tell you what the answer is. If you are just approaching a number, you're not approaching just from the left and just from the right, the answer is actually very easy. It's going to simply be does not exist. Let's take a look and see what happens if we're approaching from a side. In this problem, we have the limit as x approaches 4 from the left. So what do we do in this situation? Well, what you want to do is you want to pick a number that is to the left of 4. So I'm going to pick the number 3. Believe it or not, all we have to do is simply plug 3 into this and simplify it and see what we get. So if we plug 3 in, we're going to get the absolute value of 3 minus 4 over 3 minus 4. Now 3 minus 4 is negative 1. You'll notice that the numerator and denominator stayed the same, except that the numerator has the absolute value piece in it. That means it's going to take the numerator, it's going to make it positive, and what we're going to end up with is simply negative 1 as our answer. Let's take a look and see what happens if we approach from the right. Now we are approaching 2 from the right. So what we will do this time is we will pick a number that is to the right of 2. I'll pick the same number as last time, 3. So we're going to get 3 minus 2 over the absolute value of 3 minus 2. That's going to be 1 over the absolute value of 1, and I think you'll see that that's just going to end up being 1 here. So when you do these problems, you want to pick a number that is either to the right or to the left of the number if you're approaching from the right or from the left. And if you're simply approaching the number, the answer is going to be D and E. I want to emphasize that what I'm telling you here only works in this scenario where you have something over the same thing. Look back at the previous problems and you'll notice the numerator and denominator were precisely the same except for the absolute value bars. Let's quickly summarize the 5 different examples that we looked at here. When you get 0 over 0, there are 5 very common things that you'll do in your calculus class. The first thing you want to do, of course, is to analyze the function and see what you can do with it. If it looks like you can factor it, you should factor it. If you see square roots, you should think conjugate. If you see fractions within fractions, you'll have to think about getting common denominators and turning it into just a single fraction instead of multiple fractions. If you see trig functions, you need to be able to manipulate the trig functions. You have to be able to write everything in terms of sine and cosine and move things around and use two known limits. Probably the biggest limit is the first one, the limit as x approaches 0 of sine x over x equaling 1. That one seems to come up the most often in my experience. Finally, if you see absolute value, and keep in mind this is only true if the numerator and denominator have the same pieces, except one of them has the absolute value bars around it, you're either going to get d and e if you're just approaching a number. If you're approaching from the right, pick a number that is to the right of that number, plug it in and simplify, and you'll get your answer. And if you're approaching from the left, pick a number that is to the left of that number, plug it in and simplify, and you will also get your answer. The next thing that can happen when you use substitution is you'll get not 0 over 0. And yes, there is a difference between 0 over 0 and not 0 over 0 when you do limit problems. Consider this problem here. We have the limit as x approaches 1 of x over x minus 1. If we use substitution, we're going to get 1 over 0. Now, what this means is that you are actually approaching a vertical asymptote. When you do these problems, one of three things will happen. Your answer will be does not exist, positive infinity, or negative infinity. So how do you figure out which one is which? Well, here's what you're going to do. You're first going to draw a number line, and you're going to put the number you're approaching in the middle. Then you're going to pick two numbers that are very, very close to the number that you're approaching. The closer, the better. You don't want to pick numbers that are too far away. So what I like to do is go 3 decimals level of closeness, if you will. So over here on the left, I'm going to pick 0.999, and over here on the right, I'm going to pick 1.001. Remember, you have to pick numbers that are very close to 1. If you pick a number that's too far away from 1, like if we picked 100, this method wouldn't really work here. Okay, so what do we do with this information? Well, what we're going to do is we're going to take each of these numbers, we're going to plug it back up into here, and we're going to just see what kind of an answer we get. So let's start with this 0.999. Let's take 0.999 and plug it in for x. We're going to get 0.999 over 0.999 minus 1. Now, believe it or not, you don't need a calculator, and you don't need to figure out the exact answer over here. What you do need to figure out is your answer positive or negative? So take a look here. 0.999, of course, that is obvious. That's positive. If you take 0.999 and subtract 1 from it, that's going to give you a negative answer. That's because, right, we have a number that is just slightly smaller than 1, and then we're subtracting 1. And a positive divided by a negative is a negative. Okay, so that's what happened when we plugged in 0.999. Now let's plug in 1.001. So we're going to get 1.001 over 1.001 minus 1. So this is going to give us positive divided by positive, which of course is going to give us positive here. So what does this really mean? Well, what it means is that as we approach 1 from the left side, because we got a negative answer, that means that we are approaching negative infinity. If we approach 1 from the right side, we got a positive answer here. That means we're approaching positive infinity. Since we have two different answers here, negative and positive infinity, the final answer is going to be D and E. Now, just to give you an idea of what this looks like graphically, let's draw an xy axis. Let's put one right here. We have a vertical asymptote right here. As we approach from the left, our graph is going to be going like straight down like this. As we approach from the right, our graph is going to be going straight up like this. Since we're approaching two different values here, the final answer is D and E. If both of these had been approaching the same thing, so if they had been both pointing up or both pointing down, then your answer would have been positive or negative infinity. So this is what happens when you're approaching a number. But what happens if you're approaching a number from just one side? Let's look and see what happens as x approaches -2 from the right. First, notice that if you do plug -2 in, you're going to get not 0 over 0, because you're going to get 1 over 0. Then what we're going to do is we're going to draw a number line. We're going to put the number we're approaching in the center, and then we're going to pick two numbers that are very close to -2. So perhaps we'll take -1.999 and -2.001. Now these problems, when you're approaching from just one side, is a little bit easier than just approaching a number. That's because we only need to pick this piece over here, the piece on the right, because we are approaching from the right. So let's take -1.999 and plug it in up here and see what happens. So we're going to get -1.999 plus 3 over, and actually I'm going to pause here for a second and note that this entire piece down here is squared. So instead of plugging in -1.99 and then adding 2 and seeing what would happen if I square it, in my head I can just go, anything squared is positive. So I'm just going to write a plus here for positive. Okay, -1.999 plus 3 is itself positive, so we're going to get positive over positive, which is positive here. What that tells me is our final answer is going to be positive infinity. In fact, what's happening here is that, once again, we are approaching a vertical asymptote from the right, and as we get closer to the asymptote, our graph is going to be shooting straight up. Let's look and see what happens as we approach from the left. Now, if we had done this problem and we're approaching -2 from the left, I would have chosen -2.001. Then I would have plugged that up into here to see what happens. In that particular case, we would still have gotten a positive answer because the denominator is always positive, and -2.001 plus 3 is also positive. And if we had gotten rid of this little plus sign altogether and approached just -2, the answer would also be positive infinity, because whether you approach from the left or from the right, you get the same answer, which is positive. So the final answer would have been positive infinity in that case. Another thing that shows up pretty frequently with limits are piecewise functions. So that's functions that are broken down into pieces that look like this. Now, normally I would say to use the substitution method, but if you're going to use the substitution method, you might wonder, what exactly do I substitute into where? I mean, I know that x is approaching 2, but do I plug it into every single piece? Just the top piece? Just the bottom piece? Which one? Well, that's why we're looking at this separately, because it really requires its own separate method to solve. So whenever you see a limit with a piecewise function, what you want to do is you actually want to come over here to the pieces and label them. Let's call them 1, 2, and 3. The next thing you're going to want to do is you're going to want to draw a number line. Now, you'll see that over here, everything is happening around the number 2. So I'm going to put the number 2 down here. Then what I'm going to do is I'm going to do a quick sketch of these over here. So what I mean by that is x is less than 2 is the first one. So less than 2 means open circle and to the left. That's equation 1. Be sure to label your equations over here like I am. X equals 2 means it's just going to be a solid dot, and that was equation 2. And then equation 3 is x is greater than 2, so that's going to be an open circle going to the right, and that is equation 3 right here. The reason why we're doing this is because we want to see what happens as we approach 2. And sort of buried in here without saying it explicitly, we want to approach from both sides to see what's happening. So that's exactly what I'm going to do here. I'm going to see what happens as we approach 2 from the left and from the right. And using my little drawing I have here, I can figure out exactly which pieces I need to use in order to answer this question. So can you see that as we approach 2 from the left, it's equation 1 that I need to use. And as we approach 2 from the right, it's equation 3 that we need to use. In fact, in this particular limit problem, we don't need to worry about the second equation at all. It's the first and third equations that are the important ones. So now that I know this, I can use substitution. Here's what's going to happen. We're going to do the limit as x approaches 2 from the left. I know that's going to be the first equation up here, x cubed minus 2x. Now what I'm going to do is I'm simply going to use substitution for this particular piece here. So it's going to be 2 cubed minus 2 times 2, so 8 minus 4, which means that we get 4. Then we're going to find the limit as x approaches 2 from the right. Okay, so from the right, remember, was our third equation here, negative x minus 2 squared plus 4. If we use substitution here, we're going to get 2 minus 2, which is 0. That means this entire part here is 0 plus 4, which gives us 4. So notice that as we approach 2 from the left, we got 4. And as we approach 2 from the right, we also got 4. What that tells me is our final answer is just going to be 4 here. So let me write it like this. The limit as x approaches 2 of our function f of x is equal to 4. Now there are a couple of other things that could have happened. For example, we could have gotten a number here, like 4, and let's say we had gotten a different number, pretend it was 5. Well, if that had happened, our final answer would have been does not exist. That's because you need the right limit and the left limit to approach the same value to get the answer. Let's look and see what would happen if we're doing a limit piecewise function, but we're approaching from just one side. Let's take a look at this example here. Again, we are looking at a piecewise function, but this time we are approaching from the right. So we're going to start off the same way, which is to say that we are going to label our pieces, just 1 and 2 this time. We're going to draw a number line. You'll see that things are happening here around -3, so I'll put that right in the center. Then x cannot be equal to -3 means that we will have an open circle at -3, but everywhere else is okay, so we'll draw some arrows like this. For the second one, it says x is equal to -3, so that will be smack dab right there, and that'll be equation 2. Okay, so this time we want to approach -3 from the right. So we will come over here and we will approach -3 from the right, and you'll see it's equation 1 that we need to use. In fact, if we had approached -3 from the left, it would also be equation 1 that we need to use here. And as it turns out, equation 2 really doesn't come into the equation for finding this limit answer here. So, okay, we're now going to do the limit as x approaches -3 from the right. I know it's equation 1 here, so it's going to be negative x plus 3 squared plus 2. And if we substitute -3 in for x, this part again is going to turn into 0 plus 2, and we're going to get 2 here. Therefore, 2 is our final answer. Believe it or not, we have gone through all the different kinds of common problems you'll see if you're doing limits and x is approaching a number. We will now take a look and see what happens when x is approaching infinity. The very first thing you'll want to do is you'll want to analyze the function itself. So there are a couple of different functions that we're going to look at and how to approach them. The first function we're going to look at are polynomials. Now there are a couple different ways you can answer limits at infinity with polynomials. The way I'm going to answer them with you is to use end behavior. The end behavior depends on two different things. It depends on the degree of the function, and it depends on the leading coefficient. Depending on if your degree is an even or an odd number, and if your leading coefficient is positive or negative, will tell you the end behavior. Here's a quick summary of the end behavior here. So with that in mind, let's take a look at this next example. Here we have the limit as x approaches infinity of this polynomial. We're going to use end behavior, like I said. So the first thing we need to do is take a look at the degree, which is the highest exponent. That would be 5. Then we take a look at the leading coefficient, which is 4. So if you have a polynomial which has an odd exponent, an odd degree, and a positive leading coefficient, that tells you what the ends of the graphs are going to do. The odd exponent means the arrows will be pointing in opposite directions, and the positive leading coefficient means that the arrow will point up as you move to the right. So this right here is the end behavior of this polynomial. Now that we know this, we can go back and look and see x is approaching infinity. If you think about this like a number line, that means that x is moving in this direction, and because of our end behavior, we're always going up, which means the final answer to this problem is simply infinity. If x had been approaching negative infinity, that means that if we think about this like a number line, we would be moving in this direction and our graph would always be going down. That would therefore mean that our final answer would have been negative infinity in that case. The next thing we're going to look at are rational functions. Rational functions are where you have one polynomial divided by another polynomial. In order to see what's happening here, what you want to do is focus on the pieces that have the degree, that is the largest exponent, in the numerator and compare that to the largest degree in the denominator. Depending on what you see will help you answer the question. So let's look at an example here. Here we have a rational function. That's because we have one polynomial divided by another polynomial. So what we need to do is compare the degrees of the numerator and the denominator. So if you take a look, you'll see that we have the largest exponent being a 2 in the numerator and denominator. So this is the first thing that will happen. If they are the same, what you will do is you will take the leading coefficients of both pieces and divide them. So what we're going to get over here is 4 divided by 2, which of course just ends up being 2. Believe it or not, these questions actually can be that easy. So be on the lookout for the same degree in the numerator and the denominator. All right, but what happens if you have a rational equation and the denominator has a larger exponent compared to the numerator? Now I want to be really clear here. When you see no variables in the numerator, the degree of that part is going to be 0. So don't think that the degree here is 1. It's because there are no variables. If you really wanted to, you actually could write a variable in here. You could write it as x to the power of 0, like this. So the top has a degree of 0, the bottom has a degree of 2. Since the bottom has the larger degree compared to the numerator, our answer is very simply 0. This is even easier than the other one, I would say. So be on the lookout for a degree which is larger in the denominator, because you will always get 0. This leads us to the final case of what can happen if you're comparing the degrees. The degree in the numerator, in this case, is definitely bigger than the degree in the denominator. So what do? Well, here's what you want to do. You want to focus on whatever the term is in the numerator that has the highest exponent, and you want to focus on the term in the denominator that also has the highest exponent. So let's write that out here. We have x to the 8th over 6x squared. Then what you're going to do is you're going to try to simplify this, which we can do pretty easily, because these will cancel with this, leaving us with x to the 6th. Now, I'm going to do one extra thing here. Instead of writing this as x to the 6th over 6, I'm going to write it as 1/6 times x to the 6th. Why am I doing that? Well, because once you do this and once you simplify it, you want to go back to end behavior. So take a look here. We have an even exponent and a positive leading coefficient. So what that tells me is that no matter which direction I go, either to the right or to the left, my end behavior is going to be like this, where both arrows are pointing up. So if we come back to here and take a look, x is approaching negative infinity. That means as we move further to the left on the graph, well, as we move further to the left, our graph is always going to be going up. So that means our final answer is simply infinity. Next thing we'll look at are exponential limits at infinity. Now, depending on how these are set up, they can be pretty tricky. There are a couple of limits that you need to know with exponentials. Here they are. There's actually a total of 4 of them. Now, you'll notice that when I wrote these out, I wrote e to the x. You'll very commonly see e to the x, but it doesn't have to be e to the x. As long as it's a positive number there, it could be 2 to the x or 5 to the x. All the same ideas will still apply. So with that said, let's take a look at an example. Let's take a look and see if we can figure out this limit here. We have e to the negative x squared minus 2x minus 3. Now at first glance, this does not look like one of the things that we had just looked at. But actually, if we analyze it a little closer, you can see it actually is. So what we're going to do is we're going to focus on this exponent up here. You'll notice that all of the variables x are up here in the exponent. So sort of like separately, let's go ahead and see what happens as x approaches infinity of negative x squared minus 2x minus 3. We're going to use end behavior here because this is a polynomial. Since the exponent is even, that means the arrows will be pointing in the same direction, and since the leading coefficient is negative, it's going to be pointing down no matter how you look at it. So that means that really what we have here is negative infinity. So let's think about this for a second now. We have the limit as x approaches infinity here, and then we have e to a, let's call it a very negative value up here, like this. Does that seem to match something we've done before? Well, yes, actually. If you have e to a very negative value, like e to the negative x, let's say, as x approaches infinity, our answer is going to be 0 here. So really, what the goal was here is to try to make this look like one of those 4 previous limits that we looked at. All right, so last time we were able to make the problem look like one of our known limits. But if you look here, we actually have 2 different ideas combined into one. In the numerator, we have a polynomial here, x raised to 1 million. That seems like that'll be pretty big. In the denominator, we simply have e to the x. So what do you do in a situation like this? Well, this requires a little bit of extra knowledge. That knowledge is that exponential functions will always grow faster than polynomials, even x to the 1 million. What I'm trying to say is that there will be a point when you're plugging in x's that are getting bigger and bigger, where e to the x will guaranteed be bigger than x to the 1 millionth power. So if the denominator is growing faster and faster and faster compared to the numerator, and of course we are approaching infinity, so the numbers will continue to grow forever, that means our final answer is simply going to be 0. In fact, anytime the denominator is growing faster than the numerator, you're always going to get 0. That's why back in the rational functions, if the denominator had a larger exponent, that piece was growing faster, and thus the answer was 0. The next thing we're going to take a look at are radicals. So consider this limit down here. You'll notice that this is not a rational function anymore because a rational function is made up of polynomials. The numerator is a polynomial, but the denominator has this radical in here, so that's not a polynomial anymore. So what do? Well, believe it or not, it's going to be somewhat similar to our rational exponents thing, but there's one extra thing that you have to remember. You cannot forget this, and I cannot emphasize enough how important this is. What is the square root of x squared? Every time you do this problem, you will always get a positive answer. So what you want to do is you want to make sure it's positive by putting absolute value bars around it like this. Now I think that most students would say the square root of x squared is equal to just x. Now that is true if you're working only with positive values of x. But if you want to cover all values of x, you need to put the absolute value bars here. So you have to make sure your final answer is positive by doing this. This is extremely important, and this is going to be the difference between getting this question right and getting it wrong. So let's take a look at this question. Now that we know about this, what we're going to do is we're going to come down here and we're going to focus on the largest terms, so to speak. That is the terms with the biggest exponent, here and here. Let's write those out separately down here. We have 6x cubed over the square root of 36x to the 6th. Then what we're going to do is we're going to simplify, if possible, which we can. For example, the square root of 36 we know is just 6. And then over here we have the square root of x to the 6th, which is x cubed. Now, remember what I said earlier. Every time you do this, you have to make sure that the square root part is positive. Now 6 is already positive, so I don't need the absolute value, but x cubed, well, maybe that is negative if you choose the right x value. So we have to put absolute value bars there. Okay, now we have 6 divided by 6. That means these will just go away, and we'll be left with x cubed over the absolute value of x cubed. So we've simplified things down a little bit, but what do we do from here? Well, now we come back up to here, and we kind of see what happens. X is approaching negative infinity. So let's imagine what would happen if we plug in numbers that are more and more negative. Well, down here in the denominator, because of the absolute value bars, you're always going to get a positive result. Up here in the numerator, though, that is going to be negative because it's to an odd power. So what you're going to get if you start plugging in numbers for x, in fact, let's do this really quickly. Let's go ahead and just plug in, say, negative 10, right? We want it to be negative, so we'll do negative 10 cubed over the absolute value of negative 10 cubed. So that's going to be negative 1,000 over positive 1,000, and therefore our final answer is just going to be negative 1. Let's do another question. Okay, notice we have a square root up here. Let's go ahead and focus on the largest piece up here and the largest piece down here. Let's take those and write those down here. So we have the square root of 2x to the 12th over 3x squared. Now there is no perfect square root of 2, so I will just leave that as the square root of 2. But I can simplify this into x to the 6th, like that. Now, remember what I had said earlier. What I had said earlier is that you should always make sure your answer is positive by putting absolute value bars around it. But if you look here, x to the 6th is always positive because it has an even exponent. So we don't need to put the absolute value bars around this particular one, which is nice. It'll make it a little bit easier for us to accomplish our goal here. So what we're going to do is we're going to try to simplify now. So we have the square root on top, the 3 in the bottom, and then we have an x to the 4th here. Once we do this, we can see that this is going to be just like the polynomials. We're going to do end behavior at this point. So we have an even exponent and a positive leading coefficient. That means both arrows are going to be pointing up no matter which direction you go. So that means our final answer is simply positive infinity. If you've been following along with the flowchart, you'll notice that we're at the end here. Now I couldn't have put in every single limit problem you'll run into, but I think we covered a lot of ground here. Certainly a lot of ground of the most common things you'll see in a calculus class. So if you're studying for a limit test or just need a refresher, go ahead and use that flowchart to help you. If you found this helpful, you may consider checking out cruisingthroughcalculus.com. This is a website I've created where I have hundreds of videos that talk about the different topics you'll see in calculus, including detailed video solutions to many different problems. Until then, keep cruising through calculus.